There's one interesting consequence of the RSA theorem, which we've called here corollary to the RSA theorem, and it's the following. So here again is the statement of the RSA theorem, and if you look at all the possible w's, in other words, w bigger than or equal to 0 and less than n, they're the secret numbers, then the encrypted numbers obtained by taking w to the power e modulo n. And the corollary says that, in fact, these will all be different from one another, in the sense that if I take two different w's, then I'll get two different c's. So let's just state that as a corollary over here. We suppose, as before, that p and q are distinct primes. We take n to equal pq and m to be p minus 1 times q minus 1 as before. Now, we take e bigger than or equal to 1 less than m, just as here, and the greatest common divisor of e and m equal to 1. Now, the statement of the conclusion is that the we to the mod n are all different, and that says nothing about the number d. So we don't include anything about d in the hypotheses of this corollary. Then we must actually have a permutation of 0 up to n minus 1. So let's go for the proof. Suppose that w1 to the power e and w2 to the power e modulo n are equal. Now we introduce d. We assume that d is bigger than or equal to 1 less than m, and it's the multiplicative inverse of e modulo m. In other words, it's exactly the same as happened here in the RSA theorem. We know that there is a unique d for which this is true, just as we knew it here in the case of the RSA theorem. So, given this, if I raise each of these to the power d, as here, then we must again have equality modulo n, just by properties of multiplication and moduli. But w1 to the e to the power d is w1 to the ed, and we know that is equal to w1 modulo n by the RSA theorem. So that was the reason for introducing d. Even though the corollary says nothing about d, to prove the corollary, we introduced d. So now we have that w1 must equal w2 modulo n. But since w1 is equal to w2 modulo n, and both lie in the range bigger than or equal to 0 and less than n, they in fact are equal. That's the proof. So here is an example of the RSA corollary. We take p equal to 3 and q is equal to 11, certainly primes, multiply them, n is 33, and m in this case will be 20. And then we can take e equal to 3, because certainly the greatest common divisor of 3 and 20 will equal 1. So the hypotheses of the corollary are true. The claim is then that as w ranges over the range 0, bigger than or equal to 0 and less than 33, as in the top row here, then distinct w's will always give distinct c's. And so these numbers, which lie in the range 0 up to 32 also, and are all distinct, must therefore be a permutation of 0 up to 32. And also, we could take e to equal 7, because again the hypothesis of the theorem are true. 7 and 20 have no common divisor. So again, all of these must be distinct from one another. Now that actually was mentioned before when we discussed a possible futile attempt to crack RSA. The futile attempt, which works of course in the case of the toy problem but does not work in real life problems, is to test w to the power e for all possible w. And as soon as we get one w, which gives us the encrypted number, then we concluded that that would be the secret number. We're using in that conclusion that you can't have two different w's giving the same encrypted number. And that's what this corollary, in effect, is saying.